All right, welcome back to the part two of the chapter two. So we spoke a lot about, and generally, the smallest building blocks that were literally these atoms. What these atoms are made of: protons, neutrons, electrons, etc. And then we started to see how the number of protons, so the atomic number, dictates the properties of an element. And an element is literally what it means is how many is literally something that has the exact same number of the same nature of atoms. So it's exactly the same atoms. Like oxygen has the exact same atoms, and if basically in oxygen it has the atoms need to have eight protons, so the atomic number is eight, because that gives its chemical properties. And then we later on started to realize more that electrons are really the ones that are kind of dictating how certain elements are literally behaving, because it's them that they're basically are, let's say, interacting with other atoms, because the nucleuses of two atoms will never touch each other because they're so far away. Because remember, if we have a golf ball, which is our nucleus, our closest electron is 1 mile away. So that's why when two atoms come to each other, it's usually the electrons, because they're so far away relatively to each other. And this is really, you always how we always look at the electrons, specifically the valence electrons, the last electrons that are in the valence shell. Those ones are the ones most probably that are going to be doing a lot of the work. So starting from that, we see that a lot of atoms will start to interact with each other, and will start to basically kind of associate with each other by using energy to kind of make them stable. And those are basically, chemical bonds. Chemical bonds are literally forms of energy that help certain, let's say, atoms to come together or bridge together. So we have something called molecules, which are literally a group of atoms held together in a stable association. Then you have compounds, are molecules containing more than one type of element. So molecules is literally, if you think about it, is literally elements that are the same, that are held together. An example for this is oxygen, O2. It's two oxygens that are held together by a basically energy or a chemical bond in a stable association. So they both are stable because they're now fulfilling their octet rule, basically, which in their case is they literally have, if I'm not mistaken, 2 6. They need basically two electrons. So they're literally sharing two electrons among themselves to kind of fulfill their octet rule. So this oxygen basically now is a molecule because they're from the same element. The compound is no, it's more than one element. So is not oxygen is not a basically compound, but water is, because water is H2O. So you have two hydrogens and one oxygen. So you have more than one element. So remember that. So as we know, the atoms that are together in molecules or compounds, they're held by chemical bonds. These are certain energies that are keeping this, let's say, sharing, or this basically kind of association intact. And there's different types, which we will be talking a lot about them. So there's covalent, ionic, hydrogen bonds, hydrophobic bonds, and van der Waal bonds. And generally, the strongest one you get to see is covalent, which is then followed by ionic bonds. But let's go into details about certain specific types of these bonds. So let's take a look at ionic bonds. So as we learned a lot before, specifically with sodium and chloride, sodium basically, if we go to sodium basically I think has, so this is two, I think, yeah, it basically has 11 electrons. So if we put this together basically in their energy shells, we know that the first energy level, which basically is L, has two basically electrons, because it only has one orbital, the s orbital, so two. Then in the next energy level, which is basically, so this is the L, they basically has one s orbital and three p's, so basically two in each. That gives you eight, and basically you have one. So this one basically over here. So basically, let me go to here, sorry. So this is basically your electron. Chloride, chloride is, if not mistaken, is 17. So you have two here, eight, and then seven there. So you clearly see that sodium atoms, to be, let's say, very stable, it needs to lose one electron, because then Basically, it's then valence shell, which then becomes the L, has 8 electrons. So they're all filled. It's following now the octet rule. They're now beautifully stable. So it kind of wants to lose it. While chloride atoms, they love to gain one because they literally just need 1 electron to fulfill the octet rule in their valence shell. So in their outermost shell, they want to be completely, basically, let's say, filled in their orbitals. So what happens is that sodium will literally give that electron, and what you have is a sodium ion and a chloride ion. So this is a cation because basically remember it lost an electron, so it has a positive charge. Hence this thing over here, and then chloride here gains an electron, so it becomes an ion. So it becomes a negative charge. But what happens? Oh, by the way, what you could also say is that sodium got oxidized, it lost an electron, and chlorine is reduced, it gained an electron, so hence it has a reduction in its charge. But what happens with these sodium ions and chloride ions? They are now have different charges, and a positive charge will always attract a negative charge. And they start to create this beautiful lattice. So this lattice is this beautiful 3D geometry kind of shape. And then this literally gives you crystals. So if you literally get sodium, and then and literally chloride gas together, you're literally gonna form these salt crystals, these beautiful kind of geometrical shapes, and this is all because the sodium and the chloride now have become so attracted to each other because now the sodium is a positive charge and the chlorine is negative. So that's how they're held together. They're held together by this ionic bond, in where suddenly you have one molecule that lost an electron and the other one that gained it. So suddenly you have a disproportionate of basically charges. One is negative, one is positive, and that association of a negative and a positive charge creates a bond. So that's what literally a ionic bond means. So now let's go into more covalent bonds. Covalent bonds, it's a bit more different. It's not actually that one atom loses an electron and the other one gains, and then you have a distribution of negative, basically charges. No, it's this is where sharing is caring. You have actually elements coming together to share two or more valence electrons. So you have actually no net charge because technically there's no kind of, let's say, losing of an electron. These two atoms that are sharing it, they're not losing it, so they still have the equal amount of electrons and protons because they're not losing or gaining electrons at this point. They're satisfying the octet rule because basically they're sharing it, so they, let's say, they're kind of occupying the orbitals that don't have an electron, and they have no unpaired electron in those orbitals. So these become extremely kind of non-reactive, very, let's say, stable. That's the right word, stable. And of course, the strength of the covalent bond depends a lot on the number of shared electrons, because sometimes it can be two, but sometimes it can be three. Sometimes it can be also basically well, I think it's more, or four basically. No, it's basically two or three technically. So many biological compounds are composed with them more than two atoms. They may share two electrons or two with two or more atoms. So in many biological compounds, you actually get to see that they actually might have, like for example, carbon. If you look at carbon, carbon has 6 electrons. So two goes in your L, and then it has four. So it literally needs four shared electrons. It really needs four shared electrons. So this can be from literally another carbon, but it could also be from an oxygen. It's not per se that they have to be from this exact same atom, but it can be from more than two atoms. It can basically be literally the carbon can share from one from an oxygen, one from a hydrogen, and one from a nitrogen, for example. So this is why we actually have different types of compounds with different atoms, because they can basically come share together different atoms. So, for example, this is the covalent bonds. You have basically, this is where you have a single covalent bond where they're literally sharing two electrons. Then you have here basically a double covalent bond, in where you start having a sharing of four electrons. So it is represented by literally like these kind of two bars. And then you have a triple covalent bond, which you have a sharing of literally 6 electrons. So which is shared by literally three lines. Every line is basically two electrons being shared. But the thing about it is that this sharing is not so sometimes is not so equal, because one thing that certain atoms have is they have electronegativity. And what electronegativity means is that an atom has an affinity for an electron. It means that certain atoms they basically have a better strength in pulling electrons, and this can sometimes cause a disbalance. And what happens is that I'll give you an example. Okay, so when we look at hydrogen here and oxygen, this is basically electronegativity. So if something is low, it means it has a low electronegativity, meaning it has a very, let's say, low kind of, let's say, strength in getting an electron. But if you look at basically here, basically at the ones in red or orange, they're high, meaning that they have actually a very strong pull of these electrons. So if you look at water, hydrogen here comes in, and then you have oxygen. So clearly, oxygen will literally has a more, let's say, a bigger affinity, a higher electronegativity than hydrogen. So when they actually come in and they literally start sharing that electron, the oxygen was is going to be able to pull this electron a bit more to its kind of domain. So you create a, in some sort of way, unequal sharing of that electron, where the electron is more in the oxygen side, so hence the hydrogen has more, basically has lost a bit that electron. It's still sharing it, but it's mostly shared with the oxygen. So you create these kind of partial um, charges. They're called partial charges. So this is one thing that you have to remember. So when you actually have that, we call that polar covalent bonds. That means unequal sharing of electrons. So in the case of basically water, like I said, the oxygen is pulling more the electron towards its side a bit more. So it's kind of causing an unequal sharing. So the oxygen has a partial negative charge because now the electron is more to its side, and the hydrogen actually has a partial positive charge because it's losing a bit that electron. But then you have sometimes sharing that is completely equal. Like in the case of oxygen, oxygen is two O2s. But if you go to O2, well, O2 has the exactly same um, electronegativity to oxygen atoms, so they share it completely equally. And we call this non-polar covalent bonds, meaning that they're sharing the electrons very equally. So that's what we mean by electronegativity, and how electronegativity can give rise to nonpolar or polar covalent bonds. It depends if the electron is being shared equally or not. And that depends on the basically elements electronegativity. If they're similar to each other, then they'll share it together. If not, if one has a stronger affinity to the electron, it's going to cause a polar bond. So again, let's give this a summary. An ionic bond results when there is a transfer of electrons, so resulting in a positive and negative ions. So in the case of sodium and chloride, chloride is gaining an electron and the sodium is literally losing it. So you get a full charge, a full charge. Please do not mix it up. You're getting actually a full charge. Chloride is gaining a full electron and sodium is losing a full electron, and that is causing them to be attracted to each other to create this bond, this lattice in the case of a crystal. Covalent? No, it's the sharing of it. Okay? It's not that one atom is losing the full electron, it's not. So remember that. And in some cases, basically, that sharing is completely, let's say, equal. That's non-polar. But in some cases, it's not equal. It's partially losing that electron, and you get these partial charges. Please remember that, because these are not ions. These are basically partial charges, because the overall kind of charge is still neutral, because it's a very small charge that you're giving it. It's still negligible compared to losing a full electron. So let's go into chemical reactions. So one thing between, in general, molecules and compounds, these they will literally be constantly are going to be broken up and basically gathered up, because they're literally moving at so many speeds, and they're going to keep bumping into each other. They're going to keep breaking and creating new different types of associations, or basically bonds. So that's literally what a chemical reaction is. Chemical reaction involves the formation of breaking of chemical bonds between compounds or molecules. But you also always have to remember that when you break basically chemical bonds or in a chemical reaction, atoms are shifting from one molecule to another without any change in number or identity of atoms. Okay, you're never changing it. So let's take a look at this kind of chemical reaction, and where reactants are the original molecules and the products are basically what results. So let's imagine here you have, let's say, glucose, and then basically you have oxygen. These are guys who will keep bumping into each other until you basically start breaking and creating something new. So the beginning, the initial compounds that are literally hitting each other are called the reactants, and then basically the end result is called the products. Okay, so you clearly see here that when you break them up, you do not have any change in the number identity of atoms. Suddenly, we don't have, for example, nitrogen suddenly coming up. There's no change in the identity, and the number of atoms doesn't change. So let's imagine, look, we look at here, we started off with 6 carbons, we ended up with 6 carbons. We basically here have 12 hydrogens, we ended up with 12 hydrogens. Here basically we ended up with, so that you have 6 oxygens here, basically 12 oxygens here, so with 18. So we have 6 here, we have that also there. Yeah, we have 18 oxygens. So during these chemical reactions, no new atoms were formed, and the number of the atoms basically did not change. So that's extremely important in a chemical reaction. And these chemical reactions, how fast they are basically, let's say, they go, it all depends on three things. One is temperature, because temperature, it increases literally the mobility of these kind of compounds or molecules to kind of bump into each other more frequently, because you're giving them more energy. And when you give them more energy, they're literally moving more faster. So there's a chance for them bumping into each other. So that's how temperature can actually, increase. If you increase the temperature, you're giving more energy, you're giving more mobility towards these compounds to hit each other. Another one is the concentration of reactants and products. Makes sense, because technically, in the case of reactants, you're increasing let's say the number, and when you increase the number of these, you're increasing the chance or the probability that these reactants are going to hit each other. So you can do that. And sometimes what happens is that these reactions are reversible, so that when it's basically these hydrogens, so this water and this carbons bump into each other, they can form the rest. So now in this case, these products become the reactants, and the reactants become the products, because it's going the opposite way. So of course, the amount of products can have an influence the amount of it. And then we have catalysts, and catalysts are literally kind of compounds or molecules that kind of make these whole reactions faster by literally, increasing this kind of bumping of these kind of compounds with each other. And we will be talking a lot about catalysts a bit later on. So as I said here, by the way, many reactions are reversible. For example, in this case over here, this is, oxidation of glucose by cellular respiration. But you can literally switch this, because if you switch this becomes literally photosynthesis, and where when you have 6 water molecules and 6 carbon dioxide molecules, when they bump into each other, you can create glucose over here to oxygen. So some reactions can be actually reversed in a way, and reversed, but meaning that the products can also be then become later on reactants that will give out new products. So let's go and talk about water. And water, we're talking a lot about water because water is such an interesting kind of compound. It's not a molecule, remember? Sorry, basically it's a compound. It's really because it's made of two different elements. But in the case of water, water is literally so tied up to life. And just think about this, because if you go to a desert, in the desert, there's no really life. It's very, very little life can actually happen in a desert. But if you go to a forest that is extremely rich in water, you can see thousands of different forms of life crawling and walking around this earth. It's beautiful. This is not a coincidence because water is what literally helps us be basically alive. And why is it water? Why is it not any other liquid? Well, mostly because water is actually one of those very few compounds on Earth that actually is liquid at this low temperatures. That's more one. But two is that their chemical properties literally has given certain properties that we need to live. So, what are those chemical properties? Well, let's have a look at water, how that actually looks like. So, we see here basically this is your oxygen because it has 8 protons, and we see it's sharing 2 electrons basically with the hydrogen here and 2 electrons here basically. So, there's a sharing of 2 electrons here and a sharing of 2 electrons here, and this is what literally gets you, the water compound. But we knew if you go back and you see the electronegativity kind of scale, in the electronegativity scale, oxygen has a higher electronegativity, so a higher affinity, higher pull of electrons compared to the hydrogens. So what you see is you get a partial uh, charges because these electrons will be more to the side of the oxygen atom rather than the hydrogen. And we kind of denote these partial charges as delta. So this is why you see the delta. And in the case here of the hydrogen, which is shown here as the white ball, it's literally shown here as, a delta positive, so a partial positive charge. While in the case of the oxygen, it's a partial negative charge. And this really beautifully gives you this really nice kind of very tetrahedral kind of like pyramid with a triangle in its base kind of structure because these partial ones they will not get to each other because remember positive and positive repel each other, so you have this beautiful formation of a 104.5 angle degree kind of structure, so that gives you literally like a tetrahedron. But this basically kind of formation of a polar bonds is extremely important, and it gives literally the properties of water that bear life to us. It's literally the formation of these polar, basically bonds, but these polar covalent bonds that I was talking about. But why? Why is it? Because if you look at here, this is a water molecule. This is another one. Now this hydrogen has this little delta positive, so there's basically partial positive charge. That is going to be attracted to another partial negative charge of the oxygen of another water molecule. And what you do here is you create a different type of bond that we call hydrogen bonds. Because again, it's the hydrogen that's bonding with this oxygen. It's this positive charge that's attracted to this negative, and you create a bond. That's called hydrogen bond. Hydrogen bonds are extremely weak. They're very weak to the point that technically they're actually 5 to 10% of a covalent bond, and they're transitory, meaning that they are literally breaking up literally in fractions of a second, like way less than a second. They're literally breaking up. But strength comes in numbers. So when you have a lot of hydrogen bonds coming up, you get actually a very strong uh, bond. Because think about this as a Velcro. When you literally are zipping up that Velcro, when you have multiple kind of types of these interactions, it becomes more stronger. But if it's literally one little, let's say, two kind of this kind of Velcro kind of, let's say, strings attached, that's very weak. It's extremely weak. But when there are literally thousands of them, or hundreds of thousands, or a million or something, they become very strong. And that's the same thing that happens with hydrogen bonds, that millions of those hydrogen bonds can create a very strong bond. So this is what is like, super important. And of course, here this hydrogen bond, sure, it has occurred to between two water molecules, but it can also occur with, in this case, with other organic molecules. So you see here, for example, this organic molecule, which is butanol, it has a polar bond over here. So you have here this hydrogen atom that has a positive charge and is forming a hydrogen bond with literally another water. So you have a water and a organic molecule that has this kind of partial positive charge that is forming it. So remember that hydrogen bonding definitely happens between water molecules, but can also happen with different molecules as well, as long as you actually have these basically partial charges. But one thing that these hydrogen bonds give, and specifically in water, it gives two very important and unique characteristics. It actually makes water cohesive, and what that means is that water molecules they stick to each other, because now in the case of water, there's millions of, let's say, water molecules. They're literally sticking to each other through hydrogen bonding. So this water is binding to this one, which is most probably this is going to be bonding to another hydrogen, which is going to bond to another hydrogen, on and on and on. And when you have millions of these ones that are literally pulling each other or literally attracting to each other, you're creating tension. If I'm literally grabbing a rope and I'm pulling this rope, that rope now has tension because I am literally kind of having a bond with it. I'm attracting it to myself. Well, same thing with the water. They actually keep pulling each other, that they have some sort of tension. And this is what actually allows these insects, if you see them, able to literally float on the water, able to kind of just stand on it because their gravity is nothing compared to the cohesion here, the force of the cohesion here. So it's able to just literally not sink in or break the bonds. It's able to kind of stand on them because its gravity pull is not that much. So this is what cohesion means. And another thing, another kind of property that this kind of hydrogen bonding gives out is that water molecules stick to other polar molecules. So in the case, for example, here you have a beaker that has water. You put these straws that have different, basically, diameters. These are basically these kind of straws are literally made of glass, and glass is polar, meaning what it means that it actually has this partial positive charges and partial negative charges. So water is gonna actually bind to it because now you're creating other hydrogen bonds. So in this case over here, basically, you see the water's coming up. And of course, now here, the smaller you actually make the diameter, the more the basically hydrogen bonds you can start creating, like the more it can go up. And that's purely because of the availability of the hydrogen bonds that there is. But what this basically means, you get this capillary action, which basically means that water within a narrow tube, it can rise, it can go up, it can literally start to move up because it's getting attracted to them and it's causing them to be pulled up. So that's adhesion. But also, other than that, one beautiful thing that this hydrogen bonds and these polar basically bonds that are being formed, it really gives a lot of different properties of water. And I will be talking about six that really gives us, let's say, life. The first one, water has a high specific heat, which helps maintain temperature. So, what specific heat means is defined by the amount of heat that must be absorbed or lost by 1 gram of a substance to raise or lower its temperature by 1 degree. So that means how much, let's say, how much heat does water need to be absorb. So 1 gram of water to be absorbed to raise it to 1 degree. So that's why we say 1 calorie per gram per Celsius. So how much basically heat, so how much calories do we need that 1 gram of water is increased in temperature by 1 degree? And in the case of water, it's quite a lot. You need a lot of energy to cause the temperature of water to increase. You really need a lot of it. It's not so easily to make water change its temperature. And this is extremely important because if you look at us, 2/3 of us is constitutes of water. And there's so many chemical reactions in our body that's occurring that there's a lot of release of heat. And if water was actually, very has had a very low, let's say high specific heat, well, we would actually be burning because there's hundreds of millions of chemical reactions happening per second in our body, and those are all releasing heat. You want to make sure that the water is able to absorb it and not change its temperature. It's extremely important. Two is basically water has a high heat evaporation, and what heat evaporation is quite similar to what to basically the specific heat. It's defined as the amount of energy required to change 1 gram of a substance from liquid to gas. So in the case of water, how much energy do we need for to change 1 gram of water from a liquid to a gas? For water, it's around 586 calories. We need 586 calories to change 1 gram of water from a liquid to a gas. And this is extremely important because this actually helps cooling. When we are outside, as humans or other basically vertebrate animals, when we go outside and we literally stuck in the sun, we are getting a lot of heat. We need to lose that heat. So what we do is we release water, and once the water goes out, it's gonna absorb that heat and it's gonna disintegrate or basically vaporize. And this vaporization, because it takes a lot of energy, it's just literally going to remove it, so causing a cooling effect because it's dissipating. It's literally attracting it. Once it attracts it, it kind of removes it by literally transforming a liquid to a gas. So it dissipates it, and you get a cooling effect. So this is what helps us, dissipate heat from our bodies by literally releasing water, so in the form of sweat, and that is going to help us basically dissipate that heat into basically a gas, which is going to give us this cooling effect. Solid water is less dense than liquid water. So when we get actually water, this is how the hydrogen bonds look. They look very kind of, let's say, stuck together, very, almost on top of each other. When you basically freeze it, so if you look at basically here, this ice molecule, they're quite sparse. They're not anymore literally on top of each other. No, they're very, let's say, more separated. And this is something extremely important ecologically, because if let's imagine we go to the North Pole and you go see these kind of big, massive kind of ice glaciers. If it wasn't for that solid water is less dense than liquid, well, what would happen is that that glacier would not be floating on top of the sea. It would go down because it becomes heavier because now that has more mass. It has much more basically water molecules packed together because here they're more sparser, it's more hollow, there's more space. In this case of water, it has much more atoms basically. So that's why water is able to put them to float, because technically in mass, this is very little compared to water. So in the case of the glacier, if it has a very big mass, it can go down, and it can keep going down. So technically, what happens is that the freezing can occur from bottom to up, not from the top to bottom. So technically, everything would be frozen. So that could actually kill every single fish that's living underneath it. So that could be very dangerous for us. Another fourth one is that the polar molecules and ions are soluble in water. So when you add other polar molecules or other ions, what happens when you put it in water is that the water basically these kind of negative partial charges will literally go and start interacting with it. And we call this hydration cells, and where the water molecules are literally kind of forming a shell around these molecules. So in the case, for example, of let's say salt, as we know, salt is this nice, very literally lattice cubed kind of structure. It starts to disintegrate because what happens is that the water molecules will start to interact with the sodium, and specifically the oxygen, which has this partial negative charge, and it's going to create literally this hydration shell. So multiple of these water molecules are going to bind to the sodium and kind of create this hydration shell. And this chloride, the same thing, the partial positive charges from the hydrogen is going to bind to the chloride because they're attracted. And chloride and sodium will not actually be able to come together again because the hydration shell prevents it. You have the shell of water, hence the hydration shell, that is preventing the chloride to come back to the sodium, because now these are basically in some sort of way a bit more stable because they're kind of creating this nice bond with each other. So water actually makes things very soluble, either for ions or other molecules that also have some charge, because you create some similar effect. So water becomes extremely good solvent, And basically, anything that is becoming, literally solvizing is literally, so they're called solutes. So in the case of salt, it's the solute. The sodium and the chlorine are solutes, things that are being dissolved. Fifth is water organizes non-polar molecules. So there are a lot of basically molecules that don't have electronegativity. For example, molecules that are only consisting of carbon and hydrogens. Because carbon and hydrogen have a very similar electronegativity, they actually share very equally electrons, and you don't get the creation of partial charges. So these then become nonpolar because they're sharing things very beautifully. And these non-polar basically molecules, we call them hydrophobic because they do not like water. So hydrophobic literally means water fearing. They do not like water. So they will not actually would like to interact with water. So I'll give you an example of this is literally oils. Oils are extremely rich in carbon and hydrogens, and they do not like water. So if I take water right now and I put a bit of oil, you can really see that the oil is not mixing. It's literally just a little kind of drop that's just floating around in the water, but it's not really kind of dissolving in it. And basically, what happens is that the oil, what's happening is this is the oil molecules are literally coming together. They're kind of forced to aggregate because they don't want to interact with water. They want to interact with each other, and this property is called hydrophobic exclusion. So they're literally being excluded because they're hydrophobic. They're being pushed to this, let's say, structure because they're being pushed to aggregate with each other. And this happens a lot, you basically with DNA, proteins, or other biological membranes. In the case of DNA is hydrophobic, and when you put it in water, it's literally going to start aggregating with itself, and it creates a specific shape. And the shape that we know of DNA, this beautiful helical shape. And it's all because of this hydrophobic exclusion. So, opposite to hydrophobic, we have hydrophilic, water loving substances that are polar and form hydrogen bonds with water. The final thing is water can form ions. So when we have water, it very basically rarely, but basically what happens is that water will break down into hydrogen ion and hydrogen ion. So hydroxide and hydrogen ion. And in the case of water, in 1 liter, you get a concentration of hydrogen protons of 10 to the negative 7. And that's what helps us understand what neutrality is, because we will be learning a lot about acidic or bases, because we saw that water is basically your neutrality. So that means that hydrogens, if you have a concentration of hydrogen that is 10 to the negative 7, we consider that to be neutral. So we came up with something called a pH. pH is the negative logarithm of hydrogen ions and concentration. So pH is equal to minus log to the concentration of hydrogen. So if you put it basically here, this is basically we have the concentration of hydrogen here. If that is that, the pH gives you, if you put this into this whole formula, you get a pH that is equal to 7. So that's what we defined neutral. Anything that is basically higher in hydrogen, so basically here, for example, we consider this acidic, and anything that is basically, lower in hydrogen concentration, we consider this basic. So water really helped us understand this a lot in that kind of sense. That's one important property. So I'm going to stop here. We're going to be talking about acid and bases as the last concept a bit later.